Hello, this is Darren Pulsfer, and today we're going to learn how to use Intel's Optane DC persistent memory to create an ultra-fast file system to increase my ElasticSearch throughput and responsiveness by almost 2x. So let's take a look on what we did. First, let's take a look at the different use cases that ElasticSearch has. ElasticSearch is used for lots of different things. Primarily, people are using it for log files to detect anomalies, for cyber intrusion, things like that. But we also see mashup of public data from Twitter feeds to Facebook feeds to lots of different things. It's been used. Maybe there's events that are happening in your data center. The cool thing about ElasticSearch is it does a great job at indexing files as they're coming in or logs as they're coming in. The nomenclature that they use is primarily documents. So every document that you send in gets indexed. And because it's indexed, now I can do a lot of different visualizations off of that using several different tools that are out there today. So it's a really great way of running poor man's analytics. If you don't know what you're looking for, this might be a great way to go right out of the gun. Or if you already know a very well-known pattern for detecting things in log files or whatever, it's another great tool to use. So let's take a look at Intel's Optane DC persistent memory real quick. This is really cool technology. It gives me persistence at close to DDR4 speeds, which is really cool. It comes in a DDR4 format, and it fits right into your server, right into the DIMM slots that you already have. And there's different configurations you use to get the most optimal performance. We'll cover that a little bit later. The other thing is it comes in 128, 256, and 512 gig persistent memory modules. So you can ultimately have a 2-core or a 2-socket system with as many cores as you can jam in there. You can have a 2-socket system with 6 terabytes of RAM effectively, which is pretty cool stuff. I actually have some of this in my lab, been playing around with it for the last 3 or 4 months, and it's amazing the sorts of things you can do with it. The real cool thing is the different modes of operation that they support. So they have something called memory mode, where basically you're using your DRAM as a cache for your slower persistent memory. It's not as fast as DRAM, but it's sufficient enough that when I use it in this mode, that we get very negligible performance in like 90% of the use cases that are out there. So memory mode, it's cheaper to do it this way. I can pack a lot more things onto a server, so there's just some benefit there. App Direct mode is more interesting to me because App Direct mode means I can write an application that writes directly into the persistent memory, and then I can turn the machine off and the memory will still be there. So this is a game changer. Long term, we're already seeing hundreds of software vendors that are starting to rewrite their applications so they fit more in this persistent memory mode, which is really cool because they get automatic huge performance bumps. They're no longer talking to a database, for example, or temporary storage to be persistent. They can get persistence right away. So we're seeing new architectures, new ways of doing things out of this. Now, another really cool thing that you can do in App Direct mode is you can actually create a file system out of it. Now, I want you to think about this for a second. I can have a persistent file system. And you guys have already said, Darren, we've done this with RAM. Sure you have, but have you done it with persistent memory? So when you really do have true persistent memory here, the machine shuts down, comes back, everything's still there. So I played around with the ultra-fast file system in a couple instances. In one of my other videos, you saw what we did with Kafka by using this ultra-fast file system. And we got a 10x performance improvement with Kafka. So we decided to try the same thing with ElasticSearch. I'll show you the results here. But before we do that, I want to talk about the different ways that you populate your servers with this persistent memory. So the key here is that you're filling, to get the most performance, you marry every single DRAM that you have with a PIM, persistent memory. And the ratio of 1 to 8 is pretty good. So if I have a 16 gig DRAM DIMM, I'll put in 128 gig PIM. And you can figure out all the other numbers from that. Like 64 gig DIMM goes with like a 512. So in that realm. Now, the machines that I have, I fully loaded them with 16 gig DIMMs and 128 gig PIMs. So I'm playing around with about 1.5 terabytes of effective memory. And it works out pretty well. I'm getting some pretty incredible speeds. Now, the Linux kernel has built into it, and you can get this in Fedora 29 and above. SUSE has it. Almost all of them have these tools available. The tool is NDCTL for controlling and managing non-volatile memory devices, and then IPMCTL, which is Intel Persistent Memory Control Utility. This allows me to manage the persistent memory to do different things with it. So one of the things that I do with this using IPMCTL is I take all my persistent memory and I can divide it up and say 50% of it's going to go to memory mode and 50% go to AppDirect mode, or I can take it all into AppDirect mode. For all my testing, I decided to play around with different configurations, and I have more fun with 100% AppDirect mode because I can run a lot longer tests. I can fill those drives up. So I did that. I used IPMCTL. Go out and take a look on the net. There's lots of great articles on that and how to do it. And then I use NDCTL to create a non-volatile memory device that I then mount as a file system, which is actually really easy to do, and you can find the instructions on the blog. Now, let's take a look at some of the test philosophy that we had. So when I first started looking at ElasticSearch, I went out there and said, okay, do I have to write my own test suite? Probably not. All typical open source and modern tools today have great test suites that we use. I find ESRALLY to be a great tool. They have several different, they call them races, and tracks that you can use, and different distributions. It's a really slick tool. So just by running ESRALLY, it will install ElasticSearch for me on one server, or I can attach it to a cluster if I want, or even my own version of ElasticSearch if I'm doing development. And then I can run a car on the track, and a car just shows you how it has been configured as far as heap sizes and things like that for your test clients, and also how your ElasticSearch has been configured. And then you run those cars on tracks, and tracks are basically your test suites. So it comes out of the box with several test suites, probably close to about 10. And then I ran through all those and found some really great improvements. But I really wanted to stress this thing out. I wanted to pump in terabytes of data and see what I would get out. So I went for a track called Event Data because it was generating the data on the fly, and it generates about 1.8 terabytes of data in its test run, which is pretty cool. Okay. Now, one thing that I did, ESRALLY is all self-contained in a .rally directory, which is in your home directory. I looked at, what data should I run on my persistent memory drive that's really fast, and which one should I run on my SATA drive. And I decided to take the chicken way out, and I just put the whole .rally directory on each drive and then compared them. In reality, I probably could have divided it up and said that all the race data and the indices could go on different drives, and I might have even gotten better performance. But my goal here was not to test different configurations, but to primarily test what the effects of this ultra-fast drive would be on ElasticSearch compared to a SATA drive. So I got rid of as much variability as I possibly could. I'm not going over the network. It's all on the same machine, both the test suite and the ElasticSearch install, which that decreases any network traffic. I also did a one node cluster with no replicas because I just wanted to look at just raw speed. I know I can probably get more if I divided this up into multiple services, took advantage of multiple PMEM drives. I could probably increase it even more. But like I said, I was testing one thing. What is the effect of this ultra high speed file system? Okay. So let's get down into, I wanted to show you this. This is really cool. This is how I have it configured. I went with 100% AppDirect mode, and then I mounted this all as a file system. And because I have a 2-socket system, it actually created me 2 file systems that I could use. I only used one of them. Ideally, I could have split up my data into different drives. My data and my indices in different drives. I probably would have even gotten better throughput. Maybe that's a new test I could run. And there's a cool little command, ipmctl, which tells the persistent memory how to configure itself. Anytime you change the persistent memory, you have to reboot the machine, which makes sense because it will use all of it in memory mode or in AppDirect mode. So if I have part of it in memory mode and then I swap it out on the fly, you could be vacating a bunch of memory pages that someone was using, which would be really bad. So let's take a look at some of the results. This is running event data track and running a 16 gig heap car, which is a pretty good sized car. I used that one because it tended to get the most reliable performance for what I was testing. And these results are pretty interesting. So the SATA drive was about half as fast as my PMEM drive on median throughput. So if I looked at documents per second, I was getting almost double of what I normally got with a SATA drive. Now, if I looked at maximum, the PMEM drive was still much higher, not quite as much as 2, but there was a lot more variability in the SATA drive. The standard deviation was quite substantial compared to that in the PMEM drive. So that tells me, hey, a lot more stable, a lot more reliable and consistent results coming out of that drive. So I imagine I can even bump this number up higher if I played some tricks with splitting data in indice file systems onto different drives. So that's my throughput. That's how many documents I can shove into the ElasticSearch. And then here's my service response time. This is with 100% finish, which I really wanted to test. Some of the lower ones where 50% of all of the test finished tests in the batches that were run were like 5 or 6 times higher on the PMEM drive, or faster on the PMEM drive than on the SATA drive. Again, we're close, approaching to 2x performance, especially when I have 16 clients. It's, as you look at that number, it's 4x. And then all the way up to 64 clients running, we're still close to the 2x performance. So the one thing I want you to get out of this is this new use case that we found for this persistent memory by using it in an ultra-fast file system has a lot of benefits with very little changes to code. In fact, in most cases, no changes to code, just mounting a file system, pointing your temp space to it like we did in Kafka, and now what we've shown here in ElasticSearch. If you're interested in more information, go ahead and send me an email, and you can go out there and look for our blog to find out the recipe, and you should have a lot of fun with this.